Chapter 32. Consider this. Let's say you had a circuit with a battery, an EMF, a resistance, and a switch. What happens when you close that switch? Well, the first thing you would say is that a current should flow. And according to what we've done so far, that current should be equal to the voltage divided by the resistance. Makes sense. Well, when I close that switch, a current does flow, but you know the circuit itself is like one big loop with magnetic flux. In other words, if we consider this current flowing around as we have it set up here, counterclockwise, then that's going to set up a magnetic field through the center of that loop out towards you as you're looking at it. And hence, we're going to have a flux which goes from 0 to something finite out towards you in a certain amount of time. Hence, we're going to have an increasing flux towards you. Well, if it's possible, nature will oppose that change. And here it's possible because we have a closed circuit. So nature can set up its own flux into the page to oppose the increase in flux out of the page towards you. And that would require a back current and back voltage against the original current and voltage in the circuit. In other words, there will be a back EMF that opposes the forward EMF such that the change in current does not happen instantaneously. In fact, the current will change more gradually in the circuit. We can think of it this way. This whole process with a back EMF that opposes the front EMF and momentarily is actually equal to the voltage of the battery, we call this self-induction. Since the flux is proportional to the magnetic field, and that in turn is proportional to the current, almost by the solenoid type equation, it would be true that the change in flux is proportional to the change in magnetic field, and in turn is proportional to the change in current. So we can say then that our back EMF, our induced EMF, according to Faradays Law, is proportional to the change in flux per time. And in turn, that is proportional to the change in current per time. So when the current is changing most rapidly, which is right after we close a switch, and it's going from 0 to something, that's when the back voltage, the back EMF, is at its greatest value, and at that moment is actually equal to the voltage of the battery, so that the current doesn't change instantaneously from 0 at that moment. When we first close a switch, it momentarily is still 0 current at that moment. So the self EMF is greatest right after the switch is closed, momentarily actually equal to the voltage of the battery. For infinitesimal times, we can express this relationship of the back EMF being proportional to the change in current per time as the back EMF equal to negative some constant times the change in current per time, or the derivative of the current with respect to time. Negative means it is opposing the change in current per time, and the L value is just a constant, allowing us to express this proportionality. But we have a name for this L value. It is called the inductance. So the back EMF is proportional to the change in current per time by a value, a constant, called the inductance. The System International Unit of Inductance is the Henry, named after Henry, Joseph Henry. That's his last name. So, just as resistance, R, is a measure of the opposition to the flow of current in a circuit according to Ohm's law, voltage equals current times resistance, we have here that the back EMF, the voltage induced in an inductance, is proportional to any change in current per time. And that proportionality is called the inductance. Using Faraday's law, the average voltage should be equal to the number of turns times the change in flux through a turn per time, and we just proved that that is proportional to the change in current per time by this constant called the inductance. Well, the number of turns and the inductance are both constants, so we can actually put them into the integrals, and we would have the derivative with respect to time of n times the flux through one turn is equal to the derivative with respect to time of L times I. Integrate both sides, and we have that the total flux, the number of turns times the flux through one turn, is equal to the inductance times the current. Or we can write this and say that the self-inductance is equal to the number of turns times the flux through one turn divided by the current. This is one way where we could calculate the self-inductance of a circuit or of a device by calculating the total flux and dividing it by the current. Well, one device that we're really interested in the inductance of is the solenoid. Here we have a solenoid, and the solenoid is a core with a wire wrapped around it with n turns, and in this case it has a length L. We're going to assume that L is long compared to the radius and that the core of the solenoid is indeed air. We want to calculate the inductance. So the magnetic field through the center of the solenoid is, from chapter 30, mu naught little ni, which is mu naught number of turns per length times I. Hence the flux through the solenoid would be the field times the area, cosine 0. Mu naught number of turns per length times I times A. And hence our self-inductance of the solenoid is the number of turns times the flux through one turn divided by I, where it's going to be n divided by I, the magnetic field mu naught n divided by Li times A. We can see from this that the current will cancel out, and we have that the self-inductance of a solenoid is equal to mu naught, the magnetic permeability of free space, times the number of turns squared, times the cross-sectional area of the solenoid, divided by the length of the solenoid. That is the self-inductance of a solenoid coil. One nice thing about this result is it is only dependent upon geometric factors of the solenoid. In other words, it's dependent upon how many turns you wound. It's dependent on the cross-sectional area of the solenoid and the length of the solenoid. It's not necessarily dependent upon the current that you're applying or the flux, necessarily the flux that's going through there. It's only dependent upon the geometric factors. You can make this thing with the number of turns and the area and the length. You can make it in a factory and then put it into your circuit with a expressed value of inductance. Let's try a problem. The current in a solenoid is increasing at the rate of 10 amps per second. Cross-sectional area of the solenoid is pi square centimeters. There are 300 turns on its 15 centimeter length. What is the induced EMF opposing the increasing current? Let's calculate the inductance of the solenoid first. We're told it has 300 turns. It has a length of 15 centimeters, which would be 1.15 meters. And the cross-sectional area is pi square centimeters. So that'll be pi times 10 to the minus 4 square meters. So we have all the parameters we need. Our self-inductance is mu naught n squared area over length. Mu naught 4 pi times 10 to the minus 7, 300 turns squared, area pi times 10 to the minus 4 square meters, length 0.15 meters, gives us a inductance of 0.237 millihenries. Our EMF is proportional to the change in current per time by the inductance, and so that will be 0.237 millihenries times 10 amps per second is the change in current per time, and that will be 2.37 millivolts. So that will be the induced voltage opposing the increasing current. Well, we have this device, the solenoid, and it has a magnetic field through the center of it, it actually is storing energy in the form of that magnetic field. Let's see how much energy that might be. We know power is current times voltage. And in this case, power is the derivative of the potential energy with respect to time, or the change in energy per time. We have current. The voltage across the inductor is the inductance times the change in current per time. So let's make these substitutions, giving us a differential equations in two variables, energy and current. Both vary with time, so we have that our change in energy is equal to the inductance times the current times the change in current. This gives us two variables. We can integrate both sides, and we get that our total energy is equal to, with the IDI, integrating that is going to give us 1/2 I squared. Our energy stored in an inductor is 1/2 the inductance times the current squared. That's the magnetic energy stored in an inductor at any particular time, given the value of the current that's going through that inductor. Note how similar this looks to the energy equation being stored in a capacitor. In a capacitor, it's electrical energy, and it is 1/2 CV squared. So it's 1/2 the capacitance times the voltage squared for electrical energy stored in a capacitor. For an inductor, it's magnetic energy, and it's 1/2 the inductance times the current squared. Let's try a problem. An air core solenoid with 68 turns is 8 centimeters long and has a diameter of 1.2 centimeters. How much energy is stored in its magnetic field when it carries a current of 0.77 amps? Let's calculate the inductance first. That's mu naught n squared A over L. In this case, n is 68 turns. L is 8 centimeters long, 0.08 meters, and it has a diameter of 1.2 centimeters, so the area is going to be pi times the radius squared. So we're going to have mu naught, 4 pi times 10 minus 7, 68 turns squared, pi times the radius squared, which will be half the diameter squared, over the length, 0.08 meters. This gives us an inductance of 8.2 times 10 to the minus 6 henries. Now with a current of 0.77 amps, the energy stored is 1/2 the inductance times the current squared, 1/2 times 8.2 times 10 to the minus 6 henries, 0.77 amps squared, and that will give us, everything's SI system, 2.43 times 10 to the minus 6 joules. So that would be the energy stored in that solenoid with that current running, 2.43 times 10 to the minus 6 joules. Okay, we can possibly have mutual inductance. Changing flux from one circuit can induce a voltage in a second nearby circuit. This is called mutual inductance. If we look at the first coil, there's a magnetic field going around this solenoid and through the center of the solenoid. If we bring another coil near that, it's going to feel the flux from the first coil, and hence it will have a reaction to that, and a EMF, a back EMF reacting to the change in flux through its coil. And if it's close enough, you'll get the full flux from the first coil. So the EMF induced in the second coil is always proportional to the rate of current change in the first coil, and the mutual inductance constant, which we'll call M, will be the same for both coils. So the EMF induced in coil number 1 is equal to the negative mutual inductance, change of current 2 per time. And for that matter, the EMF induced in coil 2 is equal to negative mutual inductance, change of current 1 per time. This kind of device, where you actually induce a voltage in a secondary coil due to the first coil, is commonly used in things like a electric toothbrush, where you might have a stand, and the stand has a coil itself the toothbrush is a coil in the handle. So there's no electrical connection between the two, but you can charge your toothbrush by inductance, generating a voltage in the secondary coil, and hence charging your toothbrush that way. The unit of mutual inductance is also the same as self-inductance. It is measured in henries. Here's an example of mutual inductance of two solenoids. We have one solenoid, which is a coil, and we have a secondary coil wrapped around the first one. A long solenoid of length L has N1 turns, carries a current I1, and has a cross-sectional area A. A second coil containing N2 turns is wound around the center of the first coil. Find the mutual inductance of this system. Well, the mutual inductance will be equal to the number of turns, flux going through the secondary coil over the current of the first coil. And that's going to be equal to the number of turns 2, flux B times A over the current of the first coil. Well, the magnetic field going through the secondary coil is actually the magnetic field produced by the first coil, mu naught little n, or N1 over L times I1. That times A will be the flux, and then we have times N2 over I1. The I1s cancel out, and we end up with mu naught N1 N2 area over L. We did this for coil number 2 with respect to coil number 1, but we could have done it the other way around and we would have gotten the same result. So this could have been derived for either current. Compare this result with what we got for the self-inductance of a solenoid. Self-inductance of a solenoid was mu naught N times N area over length. This one is mu naught N1 N2 area over length. They're almost mathematically similar. It's only we have two different number of turns to use, but other than that, same kind of formula. Let's try out a problem. Calculate the mutual inductance of two solenoids for which N1 is 500 turns, area is 3 times 10 to the minus 3 meters squared, L is 0.5 meters, and N2 is 8 turns. The mutual inductance is mu naught N1 N2 area over L. Mu naught 4 pi times 10 minus 7, 500 turns for N1, 8 turns for N2. They have the same area, cross-sectional area, 3 times 10 to the minus 3 square meters, and the length is 0.5 meters, giving us a mutual inductance of 3.02 times 10 to the minus 5 henries. That concludes the first part of this chapter dealing with self-inductance and mutual inductance. We now wish to transition into LR circuits. We want to use inductance.